Okay guys, so when you open up the files, you'll see that each individual sample has its own folder labeled whatever the name was .d. When you open that, you'll find two files of interest, the ACQ methodology and also the actual file that you've actually named it, which is a very large file in itself. Feel free to have a look at some of the other files, but we'll be mostly talking about the acquire method file and the results file. So inside the acquire methods file, you'll see here that the end time here was 7.8 minutes. There's other various information in there that you can have a look at, but the other thing in here is the solvent delay, which was 1.4 minutes. So in this file, we now know that it was started at 1.4 minutes and ran until 7.8 minutes. So when you actually open up the data file, you'll see here that it's actually various information there, the scan and the time, and we just need to translate it by going data text to columns, delimiting it, hitting next here, making sure that we've got comma selected there and finishing, and now we can see that all of those commas have been removed and now everything's in nice columns and rows. So across the top there is the masses, and I'm just going to insert two new columns here, which I'm going to label up. One of those is the actual elution time, and the other one is the total ion current. The total ion current is really just the sum of the ion currents of all of these other masses. So going across is the ion currents. Now this square down the bottom, if you double click on that, you can actually get it to copy the formula to copy down. So now it's time for us to actually figure out the elution time. Now we knew from the file that it took 1.4 minutes before it took the first spectrum, because that was the solvent time, and the end time was 7.8 minutes here. So therefore we can work out that the total runtime here, or better put, the runtime is really that 7.8 minutes minus the 1.4 minutes for this solvent delay there. So that means that each scan actually took, well, the total scans took 6.4 minutes, and there was 2,207 scans in total. So each scan took 0.00229 minutes. So now we can use this to figure out the time. So the first time was 1.4 minutes, and then each time after that is the previous time plus however long it took to scan. Now I'd have to turn this into an absolute reference by putting $signs before the letter and the number, then copy this down. And now what I can do is actually plot the elution time, which ends there at around about 7.8 minutes. Plot the total ion current versus the time here, and unfortunately the dialog boxes have gone missing there in the recording, but now we have a plot of the total ion current versus elution time. That's what you usually see in a chromatograph. But there's a few other things that we can do. So for instance, we might be interested in where is our decane in this. So we can work out the molecular mass of decane by knowing that there's 10 carbon atoms, and each carbon atom, it has a mass of 12 here, and there is also 22 hydrogens. So decane here has a molecular mass of 142 grams per mole. So these weights along the top here, we can use those to our advantage. So there's our elution time, so I'm just going to select elution time, and let's scroll across here until we find 142. So that's the mass to charge ratio, so that's the mass of 147, and we can actually plot that versus a time, and I'll just move this to another worksheet here, and now we have the elution of 142 versus time. Now this big peak here, if we just select the graph and just hold our cursor over it, we'll be shown the time of this peak, and here it's 4.66 minutes. And what we can do now is just check that that is actually decane. So if we scroll through to here, 4.66 minutes, and just take a minute to find it. It's here somewhere. There it is, 4.66 minutes. So I'm just going to select all of the iron currents here for that particular time, and I'm going to select all of the masses. So now we're going to plot the masses versus iron current for each of those masses, and this will give us our actual mass spectrum. And so I've just plotted this as a scatter plot, and then I'm just going to change the type here to a column graph, and we'll get something that resembles what a normal mass spec will look like. Now we can compare this. See here, there's a very high peak there at around about 102. We can compare this against the mass spec of decane. So if we actually do a NIST web search for decane, we'll find that the first hit here is the NIST webbook. And when we open that, we find various information about decane, references and all of that sort of stuff. And we can see there that there's a section there, mass spectrum of decane. And this is what the mass spectrum of decane is. There's that 142, and we have these various other decomposition products going down. Now we can directly compare that. We can see that the highest peak there doesn't correspond to that 102 before. So that other peak, although it did have a very high 142, it's probably not decane. We can also download a spectrum here, which can be copied into Excel and plotted up, so you can do a direct comparison to a known spectrum of decane. So of course, what we still need to do here is we still need to integrate the spectrum. So there is also that tool available on the Blackboard site. The way that we actually use this tool is we copy our total line current into the blue region there with the dilution time and total line current. And then we actually need to here copy and paste our background times, and you can see that first, wrong thing. You can see that the first time there is where that orange line is where it's going to take the background, and then you can just copy and paste the exact time, and it has to be the exact time. And now here, the orange lines basically say that we're integrating between those two orange lines. And it takes off the background area and leaves behind the peak area. This peak area is the one that we're going to use inside of our calibration line, our QUT caliber plot. I hope you found that helpful, guys.